So for a carrier signal CT equals AC cos 2 pi FCT and an arbitrary message signal MT, we define the amplitude.
Sir, your screen is not visible.
Not visible. Why it's always you?
I don't know, sir.
Just a second. Let me try again because it's visible on my secondary device. So just let me try again. Hmm.
Sir, it's visible.
Shripuram, now?
No, sir.
Okay, I will. So it's Siripuram or Shripuram?
My first name is Gandhi.
Your first name is Gandhi.
Yes, sir.
Oh, sorry. I thought it was your last name. I was. Oh, okay. So, yeah, that will take some getting used to. But yes.
So now it is visible.
Okay, great. Yeah, so, okay. Because Gandhi is a well accepted last name, so calling someone Gandhi sounds rude actually. But yeah, what can we do? Yeah, anyway. So, yeah, we define the amplitude modulated. Yeah, the amplitude modulated signal ST as ST equals 1 plus KMT CT, where is known as the amplitude sensitivity factor. Fine. So now this means that if I have a time and let the white color denote CT, or so if you use if you use OneNote with light color settings, this will show up as white on black. Sorry, black on white. And let the red one denote, takes time, yeah, empty. Let this denote the message signal. Fine. And 1 plus MT times CT simply means that this CT gets amplified, so that I'll draw it here. Oh, so one MT was wrong. The choice of MT was wrong. Yeah. So this is this also or this will work under the condition that Is it just me or does this look gray instead of white? Or yeah, the newer ones look darker. Why? Why is that? Hold on a second. Yeah, this is the white. Oh, sorry, I was messing around with my laptop settings. And yeah, so yes, this is white now. So ST equals 1 plus Ka mt cos 2 pi fct. And this is under the condition that Ka mt is mod of Ka mt is always less than or equal to 1. Fine. So now under this condition, this means that if t is always less than or equal to 1, then Ka. What does this mean? Anyone? Rajesh, what does this mean? If k mod of Ka mt is always less than or equal to 1, what does this imply for 1 plus Ka mt? Rajesh?
So
Yeah,
it means
it means
k1 plus kmt always greater than one or 1.
greater than 1.
It is bounded,
Uh,
saying that it is bounded less than or equal to 2.
and anything else? So bounded is always between, so a sandwich consists of 2 slices of bread. You give
Sir,
me 1
always positive.
slice. Sorry?
Always positive.
Yes, always positive.
Sorry.
Yeah, so so a sandwich consists of 2 slices of bread. So if it's sandwiched between 2 values, you have to give me 2 values. A pizza, on the other hand, consists of a single slice of bread. So there are pizzas as well, and there are inverted pizzas as well, upside down cakes. But this one is a sandwich. Anyway, so this and hence the envelope or the amplitude of ST is always positive. So this is a quick bad. So say suppose T, this is CT, and T MT. Say this looks like a sinusoid, but it can be anything. So 1 plus KMT. The first thing this will do is this will place it above 0 depending on the value of K. And then when we multiply these two signals, we will essentially, so The red one will actually give you the envelope. Yes. So this gives you the envelope of the modulated signal. So signal is simply the carrier covered in an envelope of the message signal. Fine. So any problems with this till now?
Sir, can you repeat what will be the envelope?
Envelope Yash will be, so I'll draw it again. Somehow the touch here isn't working as well as good as it used to. Maybe this thing needs a restart or something. So I'm having some trouble scrolling. Yeah, so this. See, this is the carrier. The envelope will be this. So what you will essentially get is something like this. What I'm going to do is from last year's lecture, I'm going to paste this picture that will be helpful in understanding. Okay, so we don't have a picture here. Yes, so we have I found a picture. So just hold on. And so this is what it is supposed to look like. The picture is here, yes. So this is the time axis. So wow. This is the time axis. This is ST. So and this one is the carrier, and we are considering uh, message signal that is here mt equals cos 2 pi or am cos 2 pi, right? Now
Yes.
max of called the modulation index for fine. This is a definition. So fine. Modulation index definition. So also this ST or max of ST one plus KA right? Which means if the signal MT is symmetric in the terms of maximum or symmetric the x-axis. You mean what? You understand what symmetric about the x-axis means? That its maximum and minimum value have the same magnitude. So if its maximum and minimum value have the same magnitude, then max of ST equals 1 plus index and sorry, this, yeah. So from this, if I want to find out mu, how will I do that? I'll ask that first and then do that. Guys,
Subtract them.
subtract them and yeah, subtraction is uh, subtract them. I'll get yeah, or yeah, subtract them. I'll get it. You're right. Because there is no AC involved. Oh, this should be AC, right? AC should take. AC would have been there. Fine. Now how I'll get this? Sorry, this laptop. Some days it's simply there to embarrass me. I don't know why it's going this slow today. Oh, this is the reason. Let me kill everything unnecessary. Hold on. Yeah. So that disk usage 100% is a bummer. Slows everything down unnecessarily and confuses me. Max st equals AC times 1 plus mu AC 1 minus mu. Now componendo dividendo and max S plus min of S divided by, sorry, yes, right. Sorry about AC and yes, and further in the frequency domain, ST equals 1 plus Ka mt cos, right, SF equals am I missing anything here?
1/2.
Yes, precisely. Half equals half goes outside, F minus FC plus FC plus fine. So if say something like this is asymmetric intentionally, this is like this, then say this is No, sorry, these are minuses. Fine. Minus FC. Fine. These will be half the strength. Yeah, these will be half the strength of the true signal. And is there something missing here again?
K is there, right?
K is, yes, K is here. K is here. No, in this expression, K I forgot. Yes. So this misbehaving laptop makes me nervous, and I do all sorts of typos. Sorry. Yeah. Anyway, so this in the final figure, is there anything missing?
The two impulses.
Yes, these two impulses. So who said that? Just a second. Yeah. Who? Ashwin, did you talk about the impulses?
Sir, it
No,
was
sir.
me.
Yes. Okay. So when you get back, remind me to give you a chocolate. Yeah. Anyway, so continuing. So now we know that how an AM signal behaves in the time domain and the frequency domain. And it's good now that once we know this, so now the question is that practically when we have to generate an AM signal, how do the answer is something like that we can use a circuit that looks like this. This is empty. This is CT. This in your book is given as a square law device. Sorry, this in your book is given as a diode, but I'll write it as square law device. And because a square law device would achieve this, and this is RL, and end of story. So if it is a square law device, square law means simply that out equals, so this is V out. But practically a square law device is not possible. So we end up using things like diodes, or there is actually a multiplier that we practically use that is known as the AD633 multiplier. But V out equals whole square. So MT plus equals MT M square T plus C square T plus okay, so this won't work. This won't work because not a square law device. So we'll have to use the diode. My bad. So square law device will work in the next section, not here. Empty CT and follow it up with a diode, badly drawn diode that is. RL. Fine. So now equals MT plus CT plus CT is greater than 0. Fine. This is how a diode functions. Agreed? So now with this, let's make an approximation that MT is or smaller than CT, so that the behavior of the diode controlled totally fine. I can make this approximation. Anyone has a problem with this approximation? No. Okay, great. So with this approximation, yeah, V out T equals CT but what is CT? Right, which is greater than 0 TC is the time period, and any problems with this? Okay, since hopefully there are no problems with this, which means that ST equals CT plus MT times GT, where GT is a periodic signal, that is 1 for k minus 1 by 4 less than equal to, so Tc less than equal to T less than equal to k plus 1 by 4 Tc k plus Tc less than. Right, guys? Is that okay? Yes.
Yes, sir.
Yeah. Okay. Great. So now with this in hand, I can write GT can be expanded as a Fourier series GT equals k goes from minus infinity to infinity gk j tc. Right? So is this the only form of Fourier series that you have studied, or you have studied some other form as well? Okay, let me qualify some better. So note that GT and we note that GT is an even function. So does this help our cause? Does the Fourier series of an even function have certain properties that may help us? First of all, do you agree that GT is an even function? Gandhi, is GT even?
I don't know, sir. I mean,
Okay, so now you can see the form of GT.
yes, sir.
So when do you call a function even?
F of minus t equal to f of t.
Yeah, can you quickly try this out? Or I'll draw it for you. That will make life simpler. Yeah, minus t by 4. Simpler logic actually. It is a gate pulse controlled by cos, isn't it? GT.
Yes, sir.
GT is essentially a gate pulse controlled by cos 2 pi fct. Cos 2 pi fct, is it an even function?
Yes, sir.
Yeah, so GT is even. So anyway, I'll since I'm up already, I don't know why this thing behaves like this sometime. The pen is touching it, it's not drawing anything. Now it's working again. So minus t by 4 Tc minus 3 by 4 TC. Similarly here, TC2. Fine, so this is even. So since this function is nicely even, we can, so now what is the special property of Fourier transform for even functions? Or what is the special form of Fourier transform for not even? Yeah. What is the special property of Fourier transform for even functions, or special form of Fourier series for even functions? My bad. Okay, I'll write it for you. Agreed? Or you haven't seen this earlier? All those who have seen this form, please raise your hands. Okay, 1, 2, 3, 4. 4 people. Oh, that's strange. So I would want to go back and quickly look through your signal systems course once again. If you, this is the first time you are encountering this form, or if you feel that this is the first time you are encountering this form, to be precise. So anyway, here G0 equals 1 over T by 2 to T by 2 GT dt equals, in our case, 1 over T minus T by 2 to T by 2 so minus T by 4 to T by 4, and dt equals 1 by T to T by 2 equals half. Fine. And K equals 2 by T C C C C C C, yeah, 2 by TC minus TC by 2 to TC by 2 GT cos 2 pi K T divided by TC, or it could have been in the numerator as well. dt equals 2 by Tc minus Tc by 4 to Tc by 4 cos 2 pi Kt fine. So when we integrate this, so cos is sine or minus sine? The integral of cos. Riya, the integral of cos is sine or minus sine? Riya, okay, is she here or not? Ria is here. So Ria is the integral of cos sine or minus sine. Okay, cool. So tell her to meet me after the class. It is sine. Sine by kt by tc minus tc by 4 to tc by 4 times right. So this 2 by tc cancels. 1 upon pi k sine 4 tc cancels plus sine by 4 equals 2 pi k sine fine. So this equals right. I hope you agree with this. And with this, the final form of gt looks like half plus 2 over pi cos 2 pi fc t plus 2 over pi summation k goes from 2 to infinity minus 1 to the power k minus 1 divided by 2k minus 1, sorry, 2k minus 1 cos 2 pi fct times 2k minus 1. This beast. Now, when we try to look at this carefully,
Sir, it was 2 by pi k, so why didn't we consider k there?
where? So
So,
1, k equal to 1,
okay, sir.
simplest case. Huh. So, yeah. So, why doesn't this? Yeah, sorry. So now, based on this, yt equals mt by 2 plus AC cos 2 pi FCT by 2 plus MT by 2 MT by pi cos 2 pi FCT plus 2 by pi cos square 2 pi FCT plus MT plus cos 2 pi FCT yeah. Yeah. So times summation 2 over pi summation k equal to 2 to infinity minus 1 to the power k minus 1 divided by 2k minus 1 cos 2 pi FCT 2k minus 1. This piece. So now we only want we only want these terms, right? This is the baseband signal. We don't want this, and all of these have frequencies higher than what we want. So what do we apply in over here? Something the frequency is either too high or too low. So how do we get the kind of frequencies that we desire?
Filter band
Filter,
pass.
band pass filter. We pass this through a band pass filter, and so I'll draw the circuit. Okay, this laptop is thought formatting it would have, yeah, anyway. So I'll just paste the band pass filter from last year's notes. That would be okay. Copy and yeah. So has it come on the screen? No, those scary looking shapes came, the filter didn't. Yeah, so okay. So you guys have a class at 4, right? Some of you. Even I have a meeting at 4, so let me. Yeah. Oh, it's working. So I'll just quickly draw it, and next time onwards, I'll keep in mind to restart this thing just before the class starts so that we don't have that 100% disk usage problem. This and this empty CT and you bandpass filter and you get the generated signal. So we are running out of time. So we'll stop here and continue on Monday. Okay then guys, bye. Have a nice day all of you.
Excuse me, sir.
Yeah.
What is the deadline for coding assignments starting from lecture 5? You have only
Lecture
mentioned till lecture 4.
lecture 5 onwards. So lecture 5 onwards it's regular 1 week.
Okay.
After that lecture till lecture 4 was special case because people would take some time to learn those things. After that it's 1 week.
Okay, sir.
Okay. You want 2 weeks?
If it is possible, then why not?
So end terms it might be an issue. Towards the end of the semester it might be an issue because you would have exams and I have to finish up grading by a certain date. That is the only issue. The last ones might feel overburdened. That's why I'm making everyone share the burden. So let it be 10 days, neither 1 week nor 2 weeks. 10 days after the lecture. Fine.
Okay, sir.
Okay, great. Okay then. Bye all. Have a nice day. I'm ending the meeting.